Okay, we're looking at my write-up of the solution to the practice final exam. What I'm going to do is I'm going to go through this and uh, add to the problem explanations as I go through them to include any of our details that are not currently written up. Um, so the thing I want to point out is when I was making the final, I've chosen 10 problems taken from the homework problems that you've been given for sections 7.1, 7.2, and 7.3. So all of these types of problems will be familiar to you. So the problems that you see here in this practice final, these problems are exactly the same as the ones on the final, except for uh, certain numbers being randomized. So you'll definitely know what to expect. Um, you will have, I will create two assignments in WebAssign. Um, so final exam attempt number one and attempt number two. So these are separate assignments, um, and whichever one of these you do, if you do both of them, the best score will be counted. All will be reviewed for partial credit after the due date, which is Thursday, May 14th at 11:59 p.m. It must be completed by then. Um, so um, you will each attempt you will be given 2 hours. So on average, um, 12 minutes per problem. But some of these ones at the beginning, you want to spend less time on those, get them out of the way quickly, because some of the later problems will take more time than that. Okay, so the first few problems are just about taking a Laplace transform of a given function. So here's a function, in this case, t squared plus 3t minus 5. Anytime you have a function that is several terms added or subtracted, you can uh, transform each term individually and then add or subtract the results. So that's what's being done down here. The Laplace transform of t squared plus 3t minus 5 breaks down like this. So you can pull terms apart. Also, any constant factors you can pull out of a transform. So we'll take a transform of t squared, 3 times the transform of t, and add those together, and then subtract off 5 times the transform of 1. Now, every term here is a power of t, so we use this rule that the Laplace transform of t to the n is n factorial over s raised to power 1 greater than the power you're transforming. Um, so from t squared, you get 2 factorial, which is 2 over s cubed. And then I'm going to write this out um, in a little more detail here. So you have 3 times the transform of t, which is 1 over s squared, and then minus 5 times the transform of 1, which is 1 over s, just so you can see where all the constant factors come from. And then we can clean things up, uh, get the answer in its final form. Okay, so break down individual terms, pull out constant factors, and focus on what's left, and then combine the results using these relationships. It's a transform of a sum is a sum of the transforms. Transform of a constant times a function is a same constant times that transform. Next, problem 2, same type of problem, only now we have an exponential. So again, we'll take a Laplace transform of 1 and then add it to the transform of e to the 4t. So how do you transform an exponential? It's this rule right here. So a transform of e to the at is 1 over s minus a. So we're just going to have s minus 4 for the second term, and then 1 over s for the transform of 1, much like in the last problem. And you can just add those together. No need to simplify, no need to put over common denominator in these kind of problems. Just transform each term, combine them, get your points, and move on. The third problem is also a transform of a given function. So we break it down using linearity again. So Laplace transform of f of t will be 2 times the transform of t squared, and then minus 4 times the transform of sine 5t. So the transform of t squared, as we saw before, is 2, the power factorial, which is 2 over s cubed, and then that gets multiplied by 2 to give us 4 over s cubed. And then, actually, I'll go ahead and write that out a little more fully as well, as a intermediate step. So it'll be 2 over s cubed minus, and then for this term, the transform of a sine of a constant times t, it's this rule right here. Whatever constant is in front of a t, that goes in the numerator, and then we have its constant factor of a minus 4 in front of it. So we have 5 over s squared plus 5 squared. Okay, so that's where these come from, and then after a little bit of cleaning up, we get the final answer right here. Now, one thing that is a common gotcha is forgetting that this constant needs to go in the numerator. Now, when you're transforming sine bt, it's not really much of a problem there. I think most don't make that mistake. But when you're going backwards from an expression like this to sine bt, for instance, if you have an expression like 1 over s squared plus 3 squared, for instance, and so you might go like, oh, that's the inverse transform of that is sine 3t. No, you need a factor of 3 up top. So you have to account for that. So that's a common trap. I'm going to talk about it several times. Do not fall into it. Okay. This next problem is about finding an inverse transform. And in fact, what I was just talking about comes up in this problem. So we're taking the inverse transform of this fraction right here. And it's a good idea to break it up into two fractions and transform them, inverse transform them individually. So what I can do is break this down into 3 times the inverse transform of s over s squared plus 5 squared. I've written it in that form to fit these rules here. So anytime you have a quadratic in a denominator, like a sum of squares, if it's not as a sum of squares already, you could do completing a square to make it be a sum of squares. Then your inverse transform is going to involve cosine and sine. So here I have 3s over s squared plus 5 squared minus, and then the 10 I'm going to break down, and the reason why I do it this way is I have s squared plus 5 squared in the denominator. To fit this rule, because there's a constant on top, up top, there's no s only in the first term. Here there's no s. So I'm going to have a constant up here. That constant has to match what's down below. So I have b squared down below. I must have b up above. Make these match. So in this case, I could just factor the 10 into 2 times 5 and make it that way. But suppose I had something else. Like suppose I had 12, for example. So I would have 5 up here, and then I'd have minus 12 fifths out here to compensate. So whatever constant is being squared down here, force that constant without the squaring to be in the numerator. That way it'll fit this rule exactly. So you can always multiply and divide by what you need to make things easier for you and reduce the chance of making a mistake. So now what's being transformed fits these two rules exactly. So the first term we get cosine of 5t, and then for the second term we have, this fits exactly the rule for sine of 5t. So again, I'll keep mentioning this. Beware of this constant factor up here. Don't get tripped up by that. You might find my harping on it annoying, but at least you'll remember. Okay, next problem is also inverse transform. So here we have this rational function here. So what you want to do is, in this case, the polynomial down below will factor into a polynomial of 2 real roots. So if we break it up this way, then we see that we have a partial fraction decomposition that is needed. And the form of that will be constant over this factor plus another constant over the other factor. Now, here we have linear factors, so the numerators will be constants. If you have a quadratic, irreducible quadratic, like s squared plus 4, for instance, that can't be broken up without complex numbers, which we want to avoid, then your numerator would be a linear function. But here it's just constants. So here's your decomposition. Multiply both sides by this denominator, the entire denominator, and simplify. And what you get is the numerator is equal to your first constant times whatever is not below it, so s minus 1, and then plus b times whatever is not below it, the s plus 6. So this equation you need to solve to get a and b. And you can solve, you're allowed to substitute any two distinct values of s to get a system of equations to solve for a and b. But you might as well choose the ones that are most convenient. S equals 1 to make this factor 0, and s equals minus 6 to make this factor 0. So if you substitute these two s values, for example, if I substitute s equal minus 6, then this term will go away, and I'll have minus 6 on the left side, and then I'll have a times minus 7 on the right side. So then I just divide, and I get 6/7 for a. If I substitute s equals 1, this term goes away, and I have 1 is equal to b times 7, so b is 1/7. So that's how that solution process goes. So now, here I fill in the values of a and b, and just like with taking a Laplace transform in general, so transforms and inverse transforms, you can break up terms, you can pull out constant factors, so that's what we have here. And to inverse transform these fractions, we use the same rule that was used in a previous. Okay, recording got interrupted. Apparently when I scroll through this, it causes problems, so I'm going to handle this differently. So we're having to transform these fractions. So I'm going to fill in on this problem, rule that was used earlier. That the inverse transform of this fraction is equal to e to the at. So that's what we have down here. In this case, we have a equal to minus 6, and over here we have s equal to 1. So we apply the inverse transform, this rule, and we get e to the minus 6t in the first term times the 6/7 that was pulled out, plus e to the 1 times t multiplied by this 1/7 that was pulled out. So this rule, anytime you have a constant over a linear factor, you can always pull out the constant. You have 1 over s minus a, that transforms back to an exponential, e v a t. All right, well, we're halfway through the problems, although these last problems take longer. So now we're looking at solving differential equations using the Laplace transform. So here is our ODE with our initial conditions. So what you do is you take the Laplace transform of both sides. On the right side, you'll just have 0. On the left side, you'll have use this rule for transforming the second derivative, this rule for transforming the first derivative. So here we fill in the initial values. Y prime of 0 is 0, and then y of 0 is 1. So we have s squared y of s minus s, that goes down here for y double prime. For y prime, we have sy of s minus 1, which is y of 0, so that goes down here, and then 7 times y of s. So now you gather all terms involving y of s. Okay. So I'll fill in an intermediate step here. So on the left side, you can have s squared plus 8s plus 7, all times y of s. And then all other terms, we have minus s from here, and then minus 8. So this just comes from gathering up all the terms involving y of s and factoring out y of s from those terms. And it's always going to be a polynomial that mirrors your ODE. So you have s squared for second derivative, and then s for first derivative, and then multiplied by whatever constants. So you can always expect that to happen. So now, this minus s minus 8, we move that to the other side, and then just divide by this, and we have this here. So that's our Laplace transform of a solution. Then I've just gone ahead and factored the denominator here. Like in a previous problem, we have the partial fraction decomposition. So you have this fraction decomposes into a constant over this factor plus a constant over the other factor. As before, multiply both sides by the entire denominator of the left side, and what you get is the numerator from the left side, and then we have a times whatever is not underneath it, plus b times whatever is not underneath it. So we have this equation here. You can choose any two values of s to substitute in here to solve for a and b. Again, choose the most convenient s values, the ones that make these factors zeros. So that would be s equal minus 1 and s equal minus 7. So substituting s equals minus 1 will help you get a, because this term would go away, and you'd have minus 1 plus 8 is plus 7. Sorry, minus 1 plus 8 plus 7 on the left side, and then minus 1 plus 7, so 6 times a on the right side, so a would be 7 over 6. When you substitute s equal minus 7, the a term goes away, and you have minus 7 plus 8 is plus 1 on the left, and then minus 7 plus 1 is a minus 6 on the right. So you'd have 1 is equal to minus 6b, so b is minus 1, 6. Okay. So try plugging the s values yourself to convince yourself that these are the right values. But again, you're plugging in whatever s values will make any of these factors 0 to simplify your equations. So now I can go ahead and fill in the values of a and b into this decomposition. That's all I've done to go from here to here. And now I can take the inverse transform of both sides to get the solution y of t, which is really what I'm after. So you have pull out the constant factor 7, 6 times the inverse transform of 1 over s plus 1, and then minus 1, 6 inverse transform of 1 over s plus 7. So I'm using the same rule as before, where you have 1 over a shifted s leads to an exponential. So you have 7, 6 e to the minus t. So you're applying this rule with a equal to minus 1 in this case, and then minus 7 in this case. So then you inverse transform each fraction to get your exponential, multiply by the constant factors that were pulled out, and combine them, and now you have your y of t. Next problem, similar, except now we have something non-zero on the right side. So what that requires is taking the Laplace transform of that right side also. So what happens is you transform y double prime, you get s squared y of s, minus y prime, so that leads to a plus 1, and then minus s times y of 0, so that's where the s comes from. And then minus 5, the transform of y prime, which is s capital Y of s, minus y of 0, which is where the minus 1 comes from. There's nothing else on the left side. On the right side, we take a transform of it, so it's 8 times the transform of e to the 4t. So now you're using this rule, but in reverse. So the transform of e to the at is 1 over s minus a. So we get 8 from here times 1 over s minus 4. And then we have, so actually I'm going to fill that in. So 8 times Laplace transform of e to the 4t minus 4 Laplace transform of e to the minus t. Okay. So from e to the 4t we get 1 over s minus 4. From e to the minus t we get 1 over s minus a minus 1, so plus 1, and then it's multiplied by minus 4. Okay. So now what needs to be done is, like in the last problem, take any terms involving capital Y of S, there'll be two of them in this case, group those together and factor out the Y of S. Um, so, okay. I'm going to so what I have is s squared minus 5s times y of s. And then if I go back here, what are the other terms? So plus 1 minus s and then plus 5. So I have 1 and a plus 5, so I have 6 minus s. And that is equal to transform of the right side that we saw earlier. Okay. So that's what we wind up with. But now the 6 minus s needs to be moved to the other side. So I'm just going to go ahead and do that. S minus 6 plus all that. Okay. And then just go ahead and divide by s squared minus 5. But that could be factored. So that's all I've done here from here to here. It's just divided by this s squared minus 5s. So now we have these three fractions, but it's a good idea to combine them into one fraction, so then you only have one partial fraction decomposition to compute. It's going to be kind of a mess, but it'll make things easier later. So, so what I do here is factor out the s squared minus 5s, so I have s times s minus 5, times these other factors. And here I take s minus 6 multiplied by these two factors, s minus 4 and s plus 1. And then um, plus 8 times s plus 1, because that does not occur in the denominator here, and then minus 4 times s minus 4, because that does not occur in the denominator here. And then, just from multiplying all this out, so here, these terms come from multiplying out the first three factors here. Then I've multiplied out the 8s plus 8, and then minus 4s plus 16. Watch your distributed minuses. And then here I'm just taking like terms in powers of s and combining them, and this is my fraction that I'm now going to work with. So partial fraction decomposition, I'm going to have four terms with over constants over s, s minus 5, s minus 4, and s plus 1 equal to this messy numerator. So then I multiply both sides by the entire denominator of the left side, and I get a times whatever is not underneath it, plus b times whatever is not underneath it, and then similar for c and d. So now I have this equation that I need to use to solve for a, b, c, and d. Like before, you substitute any four distinct values of s, choose the ones that make one of these factors, s or s minus 5 or s minus 4, s plus 1, makes one of those factors equal to 0. So if you go ahead and substitute those values in both sides, watch your signs. It's just an algebraic exercise at this point, but proceed carefully. That's why you want to get the earlier problems out of the way faster, so that you can have more time to work through these. So what will happen is, because you've chosen these s values, you'll only have one non-zero term on the right side in every case. So then that'll simplify the algebra greatly. Just be careful substituting things in over here. Like when you have minus 1, you'll have minus 1 cubed is minus 1, so you'll have minus 1 here. Minus 9 times minus 1 squared is plus 1, so you'll have minus 1 minus 9. So be careful about that. So once you substitute all of these in, and then substitute those s values into these groups of free linear factors, whichever one applies, in just a division, you'll be able to get these values for a, b, c, and d. So now I'm filling in those constants. for A, B, and C, and D in this decomposition. The numbers do not always work out super nicely, so please keep that in mind. So now to transform, take the inverse transform of this, you can consider each term individually, um, and within each term, pull out the constant factor. So really what you're transforming is 1 over s, 1 over s minus 5, 1 over s minus 4, and then 1 over s plus 1 multiplied by all these constant factors. So you're going to use this rule for all 4 terms. Um, so, um, and this applies even when you have just plain 1 over s, because all that means is a is 0. So I have 12 fifths times e to the 0t, which is 1. So, so a transform of 1 over s is just 1. And then, for instance, in the second term, we have 19/15 times the inverse transform of 1 over s minus 5, so a is 5, and that will give me e to the at, which is e to the 5t. This term leads to e to the 4t. This gives you e to the minus t. Multiply by 4 constant factors, add them all up, and that's your solution. So when you have these linear factors that will lead to exponentials, if they're irreducible quadratic factors, as we'll see later further down, that's what leads to sines and cosines. All right, so for the sake of clarity, I was going to fill in these, what was actually being inverse transformed here. I will repost this afterwards. Okay. I hope I have enough room for this. So this will be 2/3. Okay. Well, it went a little long, but it still fits on the page. So, um, so you're breaking this up into 4 terms, 4 inverse transforms because you have 4 terms. Within each term, just pull out the constant factor that you have, and then what's left is what you actually inverse transform. And they're always 1 over s minus some value. So we get e to that constant times t. So here we have 0 in this case, 5, 4, and then minus 1. Okay, 3 problems to go. Here we're just finding the Laplace transform of a given function where a unit step function is involved. So here we have t times the unit step function evaluated at t minus 5. So this function is equal to 0 until t equals 5, at which point it becomes equal to t. Now the rule you're going to use is this one right here, but you have to rewrite whatever you're transforming to get it into that form. So we need this to be a function of t minus 5. So what you do is go ahead and throw in a minus 5, and then you add in a plus 5 to compensate. So now I can break this up into the Laplace transform of t minus 5 u of t minus 5, that's right here, plus transform of 5 times u of t minus 5. And a constant factor, of course, can be pulled out. So now we have these 2 terms to transform. So this fits this rule exactly with little f of t equal to t. So you take the transform of t, and that's 1 over s squared. So that leads to the first term here. And because of this rule, whatever unit step function you have indicates what exponential you have in your transform. So that's e to the minus 5s in this case. And then for the other term, I have 5 times Laplace transform of this unit step function times little f of t is equal to 1 in this case. So that leads to a 1 over s times the exponential e to the minus 5s times 5. So that's where all the different pieces come from. So whatever function you're given, first rewrite it so it's in the form as a function of t minus c for whatever c value is being used here, in this case 5. So that all you have to do is add and subtract, and then keep this t minus 5 together as you break this up into two terms, and then it will fit this rule exactly. So whatever function you have here, work with the unshifted function, which is t in this case, transform it, multiplied by the exponential. Because notice, even though this is a shifted function, the only way the value of c is involved in the transform is in the exponential, nowhere else. So again, work with the unshifted function for what you get here. Okay, and then for the other term, we're just transforming 1, and then you're multiplying the result by 5. Now for the last two problems. Oh, okay, actually this problem is also about transforming. So first we write it in terms of unit step functions and then take the transform of that. So here we have a function that's equal to t until t equals 8, and then it goes down to 0. So what happens is, right away at t equals 0, we turn on t, so that is our first term, and then when we get to t equals 8, we have to turn that function off. So we subtract off t, the function we're turning off, times a step function at t equals 8. So that way, when t is less than 8, this term will be 0. Once t is equal to 8 from that point on, u of t minus 8 will be equal to 1, and then we have t minus t, so they cancel out and give us what we're supposed to get, 0. If there had been something else here, we'd have to turn that function on, but here we're just turning off t. So this is f of t written in terms of unit step functions. So we'd like to apply the same rule as before, but because we have u of t minus 8, we must write this term as a function of t minus 8. So I do that down here. I subtract off 8 and then add 8 back in. Keep the t minus 8 together. So now I have this t was sitting here before, so it's still there, minus t minus 8 times the unit step function. And then I have minus 8 times that same step function. So here it's written in this shifted form that we need. So the rule that's being used, and I'll just make a note of that here. So, so f of t minus c, unit step function of t minus c, is e to the minus cs Laplace transform of whatever function we have here. So now Laplace transforming t, that's just a rule. Laplace transform of t is 1 over s squared. Here, we fit this term to this pattern right here. So c is equal to 8. Your function little f of t is equal to t. So we're going to have minus 1 over s squared times this exponential, e to the minus 8s. And then similar for the last term, so the function little f of t in this case is just 1. So the transform of 1 is 1 over s, and then we multiply by 8, and then because of the unit step function, multiply by e to the minus 8s. So that's where all of that comes from. Okay, so get it into a form as a function of t minus c by doing the add subtract trick, and then fitting each term to this rule. So whatever function is being shifted here, transform the unshifted version of it. So it would be just t in this case, or 8 in this case. And then multiply by the appropriate exponential in your transform to account for the unit step function. Actually, I'm going to fill in a little more detail here. So we're transforming t from the first term, and then so what we get is minus e to the minus 8s plus transform of t minus 8 e to the minus 8s Laplace transform of 1. Just so you can more clearly see where all the different pieces of these terms come from. All right, the very last problem. So now we're going to solve a differential equation that has a unit step function right-hand side and these initial conditions. If we take a Laplace transform, first I'm going to talk about the right side because that's a more interesting case here. Things like the left side, we've been doing that already. So if we fit this right-hand side here to this rule, c is equal to 1, and then little f is just equal to 1. So what we're going to have here is e to the minus s times the Laplace transform of 1, which is 1 over s. So I'm going to make a note of that here. Okay, so that's where the right-hand side transform comes from. On the left side, same rules as before. For second derivative, we get s squared y of s minus y prime of 0, which is 1. And then y of 0 is 0, so there won't be any other term here. Minus 13 Laplace transform of y prime, which is sy of s minus y of 0, which is 0. And then plus 42 Laplace transform of y is equal to what we got for transform on the right-hand side. So then, grouping all the y of s terms together, then you have minus 1, and then, minus 13 times 0, so that's all we get. So that's just cleaning up the left-hand side. And then this 1 gets moved to the other side, and then we divide by this factor here, and it leads to plus 1 over this quadratic, plus e to the minus s over s times that same quadratic. So now there are two separate partial fraction decompositions that are needed. Unfortunately, they had to be kept separate because one of them is multiplied by exponential, which doesn't really work well with partial fraction decomposition, and then the other is not. So this factors into 1 over s minus 6, s minus 7. Here, same factorization, but we have an extra factor of s in here. So here are the decompositions for each. So we have constants over the whatever linear factors that you have. So we'll just focus on getting a and b first, then deal with getting d, e, and f. Not sure why I skipped over c there. So if we're getting a and b, we have this fraction is decomposed thus, like so, and then we have that fraction is equal to these terms here. So then you can multiply both sides by the entire denominator, s minus 6, s minus 7. And we get the numerator from before, and then a times whatever it's not underneath it, plus b times whatever it's not underneath it. Again, we have two convenient values of s that we can substitute, 6 and 7. So if I substitute s equals 6, this goes away, and I have 1 is equal to a times minus 1, so a is minus 1. If I substitute s equals 7, this goes away, and I have 1 is equal to b times 7 minus 6. So 1 is equal to b times 1, so b equals 1. Same idea to get, oh, looks like my letters are off here. Okay, so that's actually D, E, and F, not C, D, and E. Okay, so here's our decomposition. Multiply both sides by the denominator, as in several other problems. And we have this equation. So we could substitute 3 values of s to get 3 equations for d, e, and f. Again, we have convenient s values, 0, 6, and 7. So if I substitute s equals 0, for instance, I get 1 is equal to d times 0 minus 6 times 0 minus 7. So a plus 42, so d is 1 over 42. And then similarly, substituting s equals 6 or 7 will make 2 out of the 3 terms disappear and lets you relatively easily solve for whatever constant is left. So substituting s equals 6 lets you get e. Substituting s equals 7 will cause these 2 terms to go away and lets you solve for f. Just watch your signs when you're substituting here. So a lot of mistakes are made at this point. So now I can fill in all my values, A, B, D, E, and F, right here. So those constants are filled in. So now for the inverse transform, I can use this exponential rule, as you can see, because like this term, 1 over s minus 6 would give me e to the 6t times minus 1. This term would give me e to the 7t. But for this part, because I have this exponential, I need to use this rule. So I need to take into account that c is equal to minus 1, and whatever I get will be multiplied by a unit step function, u of t minus 1. And then whatever functions of t these transform back to, I have to remember to shift. So whatever function of t I get, I must replace with t minus 1. So, so transforming these terms is like in other problems. We just have an exponential times whatever constant. And then everything here will be multiplied by u of t minus 1. So in WebAssign, you'd actually enter in 1 in one of the answer boxes. This part would get its own answer box. And then whatever is multiplied by the step function, this part right here, will be in the remaining answer box. So that's how the answer breaks down in terms of how you enter it in WebAssign. So in this case, I look at, I break down handle each term separately, pull out any constant factors, and then I see, well, what am I transforming? I have 1 over s here, which inverse transforms to 1, and then it's times the constant. Here I have 1 over s minus 6, so that transforms to e to the 6t, but you must replace t by t minus 1, and then don't forget the minus 1 6. Over here I have a constant times 1 over s minus 7, which transforms to, or inverse transforms to e to the 7t. Must replace by must replace t with t minus 1, and then multiply by 1/7. So that's how we get each of the terms in this inverse transform. Okay, and what I'll do is, again, break it down a little more for your reference when you look at this later, as I highly recommend. Okay. All right, so what's happening here is I have minus inverse transform over s minus 6 plus inverse transform 1 over s minus 7. Okay. Plus, and I'll do this on a separate line. And what we'll get is, because of the e to the minus s, we'll have a unit step function. So from this rule, I'll give u of t minus 1. And what's in here is going to be the inverse transform So I'll have 142 inverse transform over S minus 1/6 inverse transform of 1 over S minus 6 plus 1/7 inverse transform of 1 over S minus 7. But one thing I'm going to make a note of here that must be done once you carry out these inverse transforms is because we have t minus 1 here, what you get when you inverse transform these terms is a function of t, but you must replace t with t minus 1. So they're evaluated at t minus 1, not just plain old t. So that's how this task of inverse transforming this whole thing is broken down into individual inverse transforms based on this rule here for the part of the exponential, and then carrying out all those inverse transforms leads you to this. So again, don't forget to replace t with t minus c at the end. In this case, c equals 1. Okay, so I've come to the end. So be sure to go over this so that you can be ready for a final. I'll be putting out, I have a practice final out already, but I'll be putting out timed versions like I did with test 2, so you can make sure that you can solve the problems in the time allotted 2 hours. So best of luck, and please let me know if you have any difficulties or questions. The final will be opened on Monday, May 11th, beginning of finals week, and will be due at 11:59 p.m. on Thursday, May 14th.